All right, brilliant. Okay, so morning everybody, afternoon now. I hope everybody is well. It's really great to be able to connect with you all again. And I'm really excited to share my talk with you, modeling our landscape from space for a more sustainable future. So my research is primarily concerned with ecosystem services. And while this is a common term within academic and policy-making circles, it's not one that's widely recognized by the general public. And I find that breaking it down into these three components is a useful way of understanding it. So first, I want you all to think of the landscapes that we inhabit, all of the various habitats and land covers that occupy them. Each of these land covers is responsible for a set of processes and characteristics that help the environment function, such as habitat for animals, carbon storage, and climate regulation. And these processes occur within individual patches of those habitats and land covers, but they also happen across the landscape as well, connecting all of these different patches together. So human society depends on these processes for our survival, and their function provides us with particular benefits. And these benefits are what we call in the field ecosystem services. And this brings me on to the big question which really guides my research, which is how can models help us make better decisions regarding the supply of these ecosystem services in how our landscapes might look in the future. But today I'm going to focus on one element of my work, which relates to how the spatial scale of how these landscapes are represented influences the models of ecosystem services. So my work takes place in the United Kingdom, and it's focused on the area that you can see here, which is the Upper Welling catchment. So this is an 1,100 kilometre squared area, and it's pretty typical of a UK landscape, primarily agricultural, with pockets of woodland and human settlement. It also contains Rutland Water, which is one of the largest man-made lakes in Europe, and it's one of the UK's only inland Ramsar sites, which is a special designation given to wetlands that are of international significance. And like many places in the world, the Welling catchment is beset by environmental challenges such as species loss and habitat degradation, climate change, and also increased frequency and exposure to natural hazards. And all of these have been well documented in the area. So for example, this plot is from the British Trust for Ornithology's annual breeding bird survey, and it shows the change from the 1970 population index for several farmland bird species. And barring a few generalist species, which I've highlighted here, unfortunately, the overall picture is pretty grim, with most species experiencing significant declines, and that's primarily due to habitat loss. And here we can see the observed temperature record for the Midlands of the UK as well. And in terms of mean annual temperatures from 1884 to 2020. So across the recorded period, there's been a statistically significant increase in mean annual temperature. It's getting hotter, and with that comes numerous knock-on effects and impacts on many other elements of our environment. Our exposure to natural hazards is also increasing too. This plot from MacDonald and Sangster shows how the number of recorded flood events in the UK has increased from 1950, the sort of tail end of the plot here. And not only are the events increasing, but also the number of people that are living within at-risk areas has also increased too. So the way that this connects with ecosystem services is that maintaining healthy landscapes and the physical processes and the ecosystem services that they support is one of our best options for adapting to and mitigating against the challenges that I've highlighted, as well as many others that I haven't mentioned, because a lot of the processes that occur across the landscape help counteract some of the negative impacts of some of the environmental challenges which I've highlighted. The recognition of this relationship between ecosystem services and environmental challenges is one of the reasons that there's such an active body of research concerning modeling ecosystem services across the landscape. Many of these models rely on land cover maps derived from satellite imagery, and this is the method that I follow in my work too. So here we can see an excerpt from a satellite image from the European Space Agency's Sentinel-2 satellite. And here is the same area, but represented by the land cover map that I produced as part of my work. Essentially what I do is I analyze the radiation reflected from the surface of the Earth, and I use that to break down the landscape into areas of the same land cover type. And then each land cover class is then associated with a particular set of physical characteristics. I then use mathematical models to simulate the natural processes that occur across the landscape, using the land cover maps as the major input to these models to produce results concerning the provision of particular ecosystem services. And I think this quote from Bateman et al. Nicely summarizes why quantifying ecosystem services is now a really important goal of conservation. Essentially, the argument is that if we can make the value of ecosystem services more tangible to society, then societies may be more inclined to protect them. A really important factor of modeling ecosystem services is the spatial scale. So land cover maps, so again, the same extract I showed you earlier, and indeed any digital image is made up of pixels. And each pixel represents a little patch of reality on the ground. And they can have different sizes depending on the satellite image they were calculated from, the quality of the camera that took the image. In my map, each pixel on the map represents an area of 10 meters by 10 meters. And the size of the pixels is what Earth observation scientists call their spatial resolution. So the work that I'm presenting today is part of my comparison between 3 different land cover data sets. My map at 10 meters is the highest resolution, the finest resolution. We've got LCM 2018 from the UK Centre for Ecology and Hydrology, which is a medium resolution data set. And then CLC 2018 from the Copernicus Land Monitoring Service is the coarsest resolution data set I've used in my study. So in order to compare these 3 data sets and the effects on ecosystem service models, first thing I did was calculate 10 landscape metrics for woodland and grassland for each of the different land cover data sets. I then looked at the area of cultivated land that was represented in each map. And then finally, what I'll show you guys today is the modeled output of carbon storage calculated from each land cover data set. And that's just one of the many ecosystem service models that I'm running as part of my project. So what I want to show you now is this is an extract of my map. I've highlighted the woodland and the grassland habitats. This is an 88 kilometer squared area. All the other land cover classes I've just blanked out just so it's easier to compare here, apart from this area of water here, which is Ibrook Reservoir, just to give a bit of context. So this is my 10 meter resolution map. And as I flick through the various resolutions, I hope what you'll see is the detail in the landscape that's lost as you degrade the spatial resolution. So this is LCM 2018, the 25 meter map. So you can see some of the woodland is lost, some of the smaller patches, and also the shape of those patches becomes less complex. And then finally, we have the CLC 2018, the 100 meter spatial resolution, and you can really see the detail in the landscape that is lost as you degrade the resolution. So that's easy to see kind of visually, but landscape metrics give us numbers that we can compare to get a very definite idea. And the results of my landscape metrics analysis show that woodland and grassland are present in greater abundance at finer spatial resolutions. Those patches of the habitat are also smaller and they're more complex in their shape, and they're also more spread out across the landscape. So although it's present in a greater amount, they're not as kind of square, if you will, in their patch when you see them at higher resolution, and they're also much more spread out. And finally, what was really interesting is that the cultivated area is present in much greater abundance at coarser spatial resolutions. which you can see from this plot here. So at 10-meter resolution, the amount of cultivated area is hovering around 550 kilometers squared for the area. And then as we degrade the resolution, it's well up at over 700 kilometers squared. So essentially, when I'm creating my land cover maps from the satellite images, the smaller pixels of my data set capture more of the small linear patches of woodland and grassland present across the landscape than the coarser resolution data sets do. They miss those when they're classifying the image. These smaller woodland and grassland areas are replaced with areas of cultivated land in the classification process, which explains why that value is so much higher at the coarser resolutions. But what effect does this have on the output of the ecosystem services and the models that I'm running as part of my project? So here we can see the results of the carbon storage model performed across the 3 different spatial resolutions of data. This is probably the simplest model that I run, and it just equates the total area of each land cover class with a lookup table that contains information on the carbon stored above, below, ground, and also within the soil and the dead organic matter of each land cover class type. So as you can see, the finest resolution data set predicts much greater carbon storage values compared with the coarser data sets. Now, this model is obviously highly sensitive to the abundance of the different habitat types, and it's a good example of how much influence spatial resolution can have on model output. But just to wrap up, how does this relate to policy and where we might be going in the future? So ecosystem service modeling is here to stay, really. Governments are really keen on something called the natural capital approach now to land management, where we essentially reward landowners for providing these ecosystem services through the form of subsidies that are funded by taxes. And this is a key policy of the current government's environmental plan, Our Green Future. So we know that the spatial resolution affects the representation of the landscape from different land cover data sets, and we know that ecosystem service models are sensitive to that resolution. So what the next steps are, and what I'm working on now, are how our other models that aren't just reliant on the abundance of habitat, but also how that habitat is organized across the landscape, how will they be affected by resolution? And also, what are some of the policy implications of this? So you imagine if you're rewarding landowners for the provision of these services, if you were calculating these from 100-meter resolution data, you'd get a very different value than if you were calculating from 10 meters. So if we're looking at allocating public money for the provision of these services, we obviously want to get as accurate a picture as possible. So I'm interested in which resolution of data provides the most accurate picture. And what I'll finish my project doing is I've looked at the 2018 land cover. I'll also be modeling various scenarios for 2050 and seeing which land cover change scenario creates the best, in inverted commas, bundle of ecosystem services across the landscape. So thanks for listening, guys. Happy to take any questions that you might have.